So next topic is acceptance angle. So we have already discussed the ray theory, in which we have studied about the critical angle and the total internal reflection. Now we will discuss the acceptance angle. The acceptance angle is nothing but the maximum angle that a light can have relative to the axis of the core and propagate down through the optical fiber. So if you want to write the definition, you can write it. So this is nothing but maximum angle the light can have relative to the core of axis of core axis or axis of core, related to the axis of core and propagate through the optical fiber. So this is the definition of this acceptance angle. So we have to derive the formula for the acceptance angle. So how can we derive? So to derive this, let's consider the optical fiber. This is the optical fiber which we are considering, having some length, and suppose this is the core axis. This is the core and this will be the core axis. This is the cladding part. This portion is cladding. So this is the cladding, because we have already discussed about the structure of the optical fiber. So we know that it has three concentric cylinders. One is core and then cladding and the buffer jacket. So this part which I have hedged is called cladding, and this is the core axis and the portion, the cross section is core. Now we are saying that suppose a light is incidenting. Suppose a light, say A, is incidenting in the optical fiber, and whenever the light incident from one medium to other, it makes an angle with the normal of the boundary. So what is the boundary here? So this part is air, this part where it is, from where it is coming is air, and air is having the refractive index, suppose N0. So from this air this light is coming, and this is the core which is having the refractive index, suppose N1, and the cladding is having the refractive index N2. Okay, so now the light is coming from the air to the core. So this is another region and this is other region, and we are having the interface somewhere here which is separating the two medium. So this should be the interface, and left of this interface is air, and in the right it is core. So it is incident from core to from air to core, and this is the boundary. So the normal of this boundary is nothing but this red line which is the core axis. So it will make angle with the core axis. So let us say this angle is θ1. Now when it is moving from the rarer to denser, it moves towards the normal. So it will propagate towards the normal like this, and then it is denser to rarer. So denser to rarer, it will move away from the normal. But what is the normal here? So if you will find that the normal here, this is the core and this is the cladding. So the core and cladding is having the interface this time in this horizontal plane. This is the horizontal plane which is the boundary in between the core and cladding, and here it is the vertical plane which is the boundary between the air and core. So this time it is the boundary, so the normal of this boundary will be perpendicular to this, that is nothing but this line. This is the normal. So it will make an angle with the normal, and let us say this angle is theta c, which is equal to critical angle. So we are considering that this is the margin, or the light is traveling with this angle at the interface. So this is the marginal angle at which it is incidenting from core to cladding at the interface. Now if it is just greater than theta c, then we know that whenever the denser to rarer the light will travel, as we have discussed in the total internal reflection concept, that is, it is if traveling from the glass to air, that is denser to rarer, then if it makes angle greater than critical angle, then the complete light will be reflected back to the same medium. So we are considering the marginal value of the angle of incidence, and we are assuming that this is the angle at which the light is totally internally reflected. So the light is totally internally reflected and travels down to the optical fiber like this. It has now traveled down to the optical fiber. It will not go into the cladding part. Okay. Now suppose this angle is theta 1. So if the angle of incidence is theta 1, then the angle of reflection, so angle of reflection is suppose theta 2. Okay. So this is the angle of reflection. Now what will happen? See, this is the right angle triangle. You can see this is suppose O, this is M, and this is N, right? So in this right angle triangle, this is the horizontal line and this is the vertical line. So the angle between them is 90 degree. So the right angle triangle is OMN. Okay. So if there is a two different medium and the light is traveling from one medium to other, then we can apply the Snell's law. So from Snell's law, we can write N naught, the first medium is having the refractive index N naught, sine of angle of incidence, which is theta 1, is equal to the second medium here is N1 and sine theta 2. So this is the Snell's law, and because the air is having the refractive index 1, so it will become sine theta 1 N1 sine theta 2, because the refractive index of air is 1. Now in the right angle triangle, OMN. Okay, so in the right angle triangle, this OMN, if you will write, this value of theta 2 is nothing but 90 minus theta c, or you can also write theta c is equal to 90 minus theta 2. So this is the case, that is the angle of the critical angle at which the light is incidenting from the core to cladding and it is totally internally reflected. Okay. So up to this point it is clear to you. Now suppose there is another light, say ray B. Suppose if there is another light, suppose this is the B, and it is, as we can see from here, it is making an angle greater than theta 1. Okay. So suppose it is making an angle theta 1 dash. So here we can see that this theta 1 dash is greater than theta 1. So the angle of incidence is now greater than theta 1. Now what will happen? So as we know from the Snell's law, because the refractive index is fixed, if you will increase the theta 1, theta 2 also increases. If you are increasing the theta 1, the theta 2 also increases. Okay, so theta 2 also increases, that means it will travel like this, that is theta 2 already increased. Now what will happen? So if you find here, you can relate it from here. Since theta 1 dash is greater than theta 1, theta 2 dash will be greater than theta 2. So now whatever will be the angle, the critical angle we will consider theta c is equal to 90 minus theta 2 dash this time. And because the theta 2 is greater than the previous theta 2, and this theta 2 was the angle which is responsible for the total internal reflection, because this is the angle theta c, that means the critical angle, and we are considering that at this angle the light is totally internally reflected. So if you increase this theta 2, because it is increasing, the value of the theta 2 dash is increasing, that means this theta 2 is increasing, so it is having the negative value. So if the theta 2 is greater than theta 2 dash is greater than theta 2, then what will happen? Then this theta c dash will be theta c. That means the angle of incidence which is responsible for total internal reflection has been decreased now. So if the light is incidenting less than the critical angle, then the light will propagate, it will not totally internally reflected. That means it will be travel down to the cladding somewhere here. So the ray B is incidenting, which is making an angle greater than the theta 1, and because the value of incidence, angle of incidence has been increased, when the angle of incidence is increased, the angle of refraction is also increased. So this theta 2 also increases, and when this theta 2 increases, the critical angle decreases. So the value of angle of incidence here going to be decreased than theta c, and if the light is making an angle less than critical angle, then it will propagate to the next medium, it will not be totally internally reflected. So if it will not totally internally reflect, then what will happen? It will travel down to the cladding and it will distort somewhere here, distorted somewhere in cladding. Somewhere in cladding it will be lost. We can write lost somewhere in cladding, not distortion, word will not be good, lost somewhere in cladding. Okay, so now we have got the value that this theta 1 is the maximum angle at which the light can incident and can travel through the core of the optical fiber, propagate through the core of the optical fiber. You can write here in the definition, core of optical fiber. That would be more appropriate, right? So we consider the light A, which is incidenting with angle theta 1, and this theta 1 is the maximum angle at which the light can incident and can travel through the core of the optical fiber. So this is the light A which is incidenting and then can travel through the core of the optical fiber. If you consider there is other light which is making an angle greater than theta 1, when the light B is incidenting making an angle greater than theta 1, then what will happen? Then this theta 1 dash increases, and when theta 1 dash increases, the angle of refraction also increases, and when angle of refraction increases, this theta c is decreases, and when this theta c is decreases, what will happen? The wave will travel, the light will travel down to the cladding part and it will lose somewhere in the cladding part. So from here we can say that this theta 1 is the maximum angle that can be accepted by this optical fiber. Okay, so with the same angle theta 1, the light can incident from this side also. With the same angle theta 1, the light can incident from this side also. So it is also making an angle theta 1, and that is why it is making a cone like structure, and which is having the angle 2 theta 1, and this is known as acceptance cone. This is known as acceptance cone. Now we will derive the relation for the angle of acceptance. So theta 1 is equal to theta A. We are denoting it by theta A, which is acceptance angle for light A. So what will happen from here? This sine theta A is n1 sine theta 2, and this theta 2 can be written as sine 90 minus theta c. From here 90 minus theta c, and sine 90 minus theta c can be written as cos theta c, and it can also be written as root over 1 minus sine square theta c. So this is all sine theta A. Now we know the formula for the critical angle. So the critical angle is given by sine inverse the second medium divided by first medium, and this critical angle is between which medium? Between the core and cladding. So the second medium, the light is incidenting from the core to the cladding. So the second medium is cladding, which is having the refractive index n2, and the first medium is core. So it is n2 by n1 whole square, because this is sine square theta c, right? Now after solving this, it is n1, right? This is n1. So after solving this, we will get root over n1 square minus n2 square. So this is known as numerical aperture. This formula is for numerical aperture. This is root over n1 square minus n2 square, or sine of acceptance angle is numerical aperture. This numerical aperture is defined as numerical aperture is what it denotes. So it gives, or it defines the light gathering property of optical fiber. Light gathering property of optical fiber. And what is the acceptance angle? Then the formula for acceptance angle is theta A is equal to sine inverse numerical aperture. Numerical aperture can be denoted by NA. So we have got the two formulas. One is for the numerical aperture, which is root over n1 square minus n2 square, and another is for acceptance angle, which is sine inverse numerical aperture. Now we can also define one more formula, which is known as relative refractive index difference. Relative refractive index difference, it is denoted by delta and it is given by n1 square minus n2 square divided by 2n1 square, and n1 square minus n2 square, from here we can write this is numerical aperture, so this is nothing but the square of numerical aperture and 2n1 square. So the numerical aperture can also be written in terms of relative refractive index difference, which is Na equal to n1 into root over 2 delta. So numerical aperture can also be calculated with the help of relative refractive index difference and the refractive index of core. So this is all about the acceptance angle and numerical aperture.